Welcome to The Explainer. Today, we are diving straight into the world of digital electronics to tackle a really common puzzle. How do you take this complex, kind of messy digital logic and make it clean, simple, and elegant?
So just look at this. On the left, you've got this beast of a logic equation. If you wanted to build that in a real circuit, you'd need a whole bunch of logic gates. But then, look over on the right. That's its beautifully simple equivalent. And here's the wild part. They do the exact same thing. One is just so much more efficient.
So, the big question is, right, how do we even do that? How do we perform this incredible simplification? And this isn't just for fun. Simplifying equations like this saves actual physical space on a circuit board, it cuts down on cost, and it saves power in basically every electronic device we use. Well, we do it with this brilliant visual tool called a Carnot map. It's this awesome method that turns what looks like a scary algebra problem into a simple game of just recognizing patterns. Okay, so let's get into it. A Carnot map, or a K-map for short, is really just a truth table. But it's been cleverly rearranged into a grid. So instead of a long, boring list of ones and zeros, we get this visual map to play with. So once we have our logic equation, we take its outputs, all the ones from its truth table, and we plot them right onto this map. From here on out, our mission is super simple. Find those ones and circle them in the biggest groups we possibly can. Now, this is where the magic really kicks in. It's not just about circling ones randomly, it's how we group them. You could say this is the secret weapon of the K-map. You know, the whole process really just boils down to these 4 steps. You find ones that are next to each other, you circle the biggest group you can, but they have to be in sizes of 2 or 4 or 8. And then, and this is the absolute key, you look inside your circle for the one variable that flips, from a 0 to a 1 or back again. That's the one you get to just eliminate. Let's just walk through a quick example. So here we have 2 ones right next to each other. Now, notice that inside this circle, the variable a stays the same. It's always a 1. But look at b. It goes from a 0 to a 1. And because it changes, it's actually not essential for this outcome, so we can just get rid of it. The entire equation simplifies all the way down to just y equals a. That's it. And this quote, it really nails the core idea. You could almost think of it like a little rule in your head. If a variable can't make up its mind inside a group, if it flips its value, then it's not essential, so it goes away. That's the powerful insight that makes this whole thing feel so intuitive. Okay, so we've got the basics down. Now let's see how this thing scales up. Because when the maps get bigger with more variables, the same rules apply, but the moves we can make get even more powerful. So to really get good at this, just remember these rules of the game. Your main goal is to make sure every single one on the map is covered by a circle. And you want to make each circle as big as you possibly can, as long as its size is a power of 2. And finally, you want to do all of that using the fewest number of circles possible. And this is where it gets really good. A group of 2 ones lets us eliminate one variable. But a group of 4? Oh, that's even better. It lets you eliminate 2 variables at once. So the bigger the group you can make, the simpler your final logic becomes. All right, here's a pro tip that unlocks some really clever moves. You have to imagine the map isn't just a flat square. Think of it like it wraps around into a tube. The left edge is actually neighbors with the right edge, and the top is neighbors with the bottom. This means you can group ones on totally opposite sides of the map, which is a move that's so easy to miss. But hang on, what about those situations where certain combinations of inputs are just impossible? Like, they'll never actually happen in the real world. Well, that's where we can get even smarter with something that's kind of like a power-up. These are called don't care conditions, and we mark them with an X on our map. An X is basically a wild card. You can decide to include it in a group to make that group bigger, treat it like a 1, or you can just ignore it and pretend it's a 0 if it doesn't help you out. It's a completely free choice to help you optimize. And just look at the huge difference this can make. On the left is the equation we'd get if we ignored the X. But on the right, by deciding to include that X in our group, we were able to make a much bigger circle, which gives us a way simpler final equation. And this, right here, is the final payoff. This is why we do all this. A simpler equation means a simpler physical circuit. That means fewer logic gates, less wiring, lower cost, and less power. That's the whole point of logic minimization. What this all really shows is that sometimes the most powerful solution to a tough problem isn't about doing more complicated math. It's about finding a totally new visual way to see the problem. It kind of makes you wonder, right? What other beasts out there could become beauties if we just had the right kind of map to guide us?